All right, Evna code day 18. We're doing it in Rust. Today's problem is called Snail Fish. You ready for this, Dom?
Let's see. I didn't even notice. What can you click on Snail Fish?
Yeah. Let's take a look at this before we get started. Yeah, it's important to get these out. Oh my god, that is. There used to be this
like, I was saying it's like the blobfish where it turns into mush when it comes to the surface.
It looks kind of like that. There used to be this Tumblr, or maybe it was just a Twitter account, and it was called like Russian deep sea fishermen. And there would be all these like horrors from the deep that they would take pictures of, like from the movies.
I can only imagine.
Snailfish or sea snails. I feel like there are already things called sea snails. I feel like you can't just like reuse that name liberally.
Unless it is a sea snail.
No, I mean, they're actually mollusks. They're actually snails that are in the sea.
Oh.
Right? Well, I guess a conch is a sea snail. Right? It just like looks like a snail, but it just like is underwater. I feel like you can't just like you can't just pick meanings for words. I don't mean to be a prescriptivist, but like they have meaning.
Honestly, naming shit in the sea, they seem to have forgotten that, because like sea cucumbers are also a very poorly named creature.
They are. Also a delicacy in many Cantonese restaurants.
Interesting. I didn't know anyone ate those.
Yeah.
I'm not surprised. People eat almost everything from the ocean, so I buy it.
They're not my favorite. When I have had them, I texturally, it's a very Cantonese texture, kind of chewy and squishy. These are widely distributed from the Arctic to Antarctic oceans, including the oceans in between. So they're everywhere, basically.
That's all water.
That is the whole box of donuts.
You might as well say they live in water.
Yeah. There are many undescribed species. That's cool. Tadpole-like bodies, similar in profile to the rat tails. I don't know. They didn't say
undescribable. They said undescribed.
Undescribed species. I guess there's just a bunch of species of these things, but they look all different. Like this looks like a kind of almost like a regular fish, right?
Mm-hmm. That's just a fish. Yeah.
Okay. Cool. They sort of have like
I've learned my fish fact.
They sort of have these like kind of like indistinct profiles where they don't really have like pronounced fins. You know what I mean? So that's snailfish. And they claim that they saw the sleigh keys. They'll even tell you which direction the keys went if you help one of the smaller snailfish with his math homework. I love helping kids cheat. Snailfish numbers aren't like regular numbers. Instead, every snailfish number is a pair, an ordered list of 2 elements. Each element of the pair can either be a regular number or another pair.
Okay.
Oh god, these are it's like these are like Lisp lists. Pairs are written as XY, where X and Y are the elements within the pair. Here are some example snailfish numbers, 1 snailfish number per line. Okay, makes sense so far. The snailfish homework is about addition. To add 2 snailfish numbers from a pair from the left and right parameters of the addition operator. Oh, to add 2 snailfish numbers, form a pair from the left and right parameters of the addition operator. For example, 1 plus 2 plus 3, 4, 5 becomes, okay, so it's like a array addition or something like that. Or make a new pair, right? There's only one problem. Snailfish numbers must always be reduced, and the process of adding 2 snailfish numbers can result in snailfish numbers that need to be reduced. To reduce a snailfish number, you must repeatedly do the first action in this list that applies to the snailfish number. If any pair is nested inside 4 pairs, the leftmost such pair explodes.
That's exciting.
If any regular number is 10 or greater, the leftmost such regular number splits. Once no action in the above list applies, the snailfish number is reduced. When they say leftmost, do they mean like the leftmost node in the tree? This is like a binary tree, right? Do they mean like the leftmost if you were to draw out the binary tree.
If any pair is nested inside 4 pairs, it's the leftmost such pair. So I think it is the leftmost pair that is nested in 4 pairs.
Right, but by leftmost, oh, they just mean leftmost in if you're just like reading the number left to right. Is that right?
Yeah. Mm-hmm.
Okay.
I guess if the thing that was nested 4 levels deep was a pair of pairs, only the left side explodes. That's how I read that.
Once no action in the list above applies, the snailfish number is reduced. So I think what it is like if a pair is nested inside 4 pairs, it's after you apply these steps, you have to apply them in a loop until neither of them apply, right?
Correct.
And so theoretically, you're never going to have, after you're done processing or reducing these numbers, you're never going to have a pair that is nested inside 4 other pairs, right? Because you'll just apply this rule over and over again until they're all gone.
That's right. I'm looking at the examples above that too, and the longest number they gave, I think the max nesting is 3 deep in both of those.
Right.
So that's already been reduced. So those are valid numbers. Okay. Yep.
Yeah, because this one is a pair that is nested inside 3 other pairs, right?
Mm-hmm. Mm-hmm.
And I think the reason why they don't just say get rid of all of the pairs that are nested inside 4 pairs is that you have to apply this rule first before you go on to the next
That's right.
like 4 deep pair, right? So there's like a subtle ordering thing that they're trying to enforce here, right? Which is why we have this like leftmost rule. Mm-hmm. During reduction at most one, okay, so this is basically what I'm saying. During reduction at most one action applies, after which the process returns to the top of the list of actions. For example, if split produces a pair that meets the explode criteria, okay, explode is the first one, split is the second one. The pair explodes before other splits occur. To explode a pair, the pair's left value is added to the first regular number to the left of the exploding pair, if any. I'm already lost. The pair's left value is added to the first regular number to the left of the exploding pair, if any, and the pair's right value is added to the first regular number to the right of the exploding pair, if any. Exploding pairs will always consist of 2 regular numbers. Then the entire exploding pair is replaced with the regular number 0. Here are some examples of a single explode action. Okay, so 9-8, that's here, becomes 0-9. So what happened here? The pair's left value got added to the first number to the left of the exploding pair, and there's nothing there, right?
So it's gone. It's
gone. The pair's right value is added to the first regular number to the right of the exploding pair, which is this 1 here, right? So 8 gets added to 1, and so this 1 becomes 9. And then the entire exploding pair is replaced with 0. So that's why we have a 0-9 here. Okay.
Okay, I'm glad they gave examples because the paragraphs above were nearly impossible to understand.
Yeah. So this is an interesting example here, right? Where 3 gets added to this 4, which becomes 7, and 2 gets added to 1, and this 1 becomes 3, and then this 3-2 becomes a 0. Okay, I kind of get that rule. To split a regular number,
it's the leftmost. It's the nearest regular number by the left. Is that correct?
Yeah. This might actually be a good write this out thing. Let me grab my iPad real quick. I'll be right back.
Okay, cool. Yeah, I agree.
The reason why I want to draw this out is I think this is a tree problem, and I think drawing the actual tree helps with these.
Yeah, we're gonna have a tree that has really strict left and right ordering, which is interesting.
My desk is tiny, and it is a mess of cables at this point. I don't know if I should be using Miro to let you draw, but let's.
No, it's okay for this.
Okay. It's so funny that QuickTime is the way to do this.
It's never made any sense to me.
Yeah. Not a screen recording, Jeff. It is a new movie recording. Do you remember all this stuff?
It's been a minute.
Yeah, this is when we're doing like a pathfinding in our WebGL game. Yeah.
Oh yeah, bring back the A-star.
Okay. Let's pop this sucker over to the side. Probably don't want to draw in blue on top of a black background, right?
No, I think not.
Okay, let's take this example actually, because this one's interesting, right? What does the actual tree look like? Looks like we got a node at the top. And then, which one did I highlight? Is this one, right?
Yeah.
And then we got a node here, and then we got a 6. And this one's a node. And we got a 5. This one is a node. We got a 4. And this one is another node. And then we got a 3, and we got a 2. And then where's our 1? Our 1 is all the way up here, right? Does that look correct to you?
Yeah, I think so. Okay, and then I'm just counting 1, 2, 3, 4. Okay, and then there's node that's 4 steps down the tree. Yep. Okay.
So the algorithm for finding the leftmost leaf, or the leaf that is to the left of you, like let's say we're exploding this pair down here, right? The 3 and 2. Well, first of all, how do we know that the 3 and 2 is there, right? We could track the depth of every node.
I think we might want to.
Yeah.
Like we insert and know its depth. Split is gonna, I guess we have to like create a mapping, and then splitting is going to make it, splitting and exploding makes it pretty easy to like, keep that mapping updated. So yeah.
Right.
Okay.
I mean, the other thing we could do is not encode this as a tree, and we could just have an array of numbers and a parallel array that tells you the depth of those numbers. And then that would make it easier to find the leftmost number, or the number to the left. I'm not sure which I prefer. The tree one seems a little bit more explicit, but it also makes finding stuff to the left and right not hard. It's just more code.
Makes finding stuff to the left or right. Right, because we'll have to keep track of parent node.
Right. So the nesting level is 0 here. it's like 0 here. The nesting level is 1 here. The nesting level is 2 here. Nesting level is 3 here. And the nesting level is 4 here, right?
Yep. And it should
And
be
if-
impossible. I mean, I guess we could be given one that has depth 5, but we should never see 5, right?
We should never see 5. Yeah.
Yeah.
In fact, I think it's kind of like a little bit unclear if it's nested 5 deep.
What you do?
Because do you start with unnesting the parent of that, or do you unnest the child? Do you explode the parent that's at 4 deep, or do you explode the 5 deep one? I think it's probably the former, but like they're probably not going to give us that input, I'm guessing.
Mm-hmm.
So we could just like, if we want to find the leftmost pair that is 4 deep, we would basically do a depth first traversal biasing towards the left child, right? And accumulate the depth that we're at. And as soon as we find basically, as soon as we find this pair, we explode it. And to explode it, we take this number 3, and we need to add it to the number immediately to the left of that, if there's any.
The nearest left regular number.
Mm-hmm. So what we do is we go up a level. We go up to the parent and then do a depth first search, biasing to the left side again, looking for a leaf node, right? So we basically pop up one level and then do a depth first search from there, looking for a regular number. Biasing to the right, actually, right? We'd bias to the right.
Yeah, I'm sure. Any pairs nested inside. Trying to figure out, like, if you're exploding something, if there can ever be a pair to the left or the. There's like a bunch of hidden constraints in this one.
Yeah. I think if you bias to the, it might be the case that you would never go right, but I think if you bias to the right, it would be. You just need to make sure that you don't recurse over the thing that you're coming from, right?
Yep. Okay.
And then find the rightmost number. You would do the same thing. Actually, the rightmost number one is an interesting one. So let's say we're considering this 2, or not the rightmost, the number that's immediately to the right of 2. If we were trying to do this from like a tree perspective, you'd bubble up one level, and then you'd say, okay, I don't want to go backwards. So how do you know that you're not going backwards?
You need to know that you came from the right to be able to say that, and it's.
Yeah. Okay, let's try the other idea then. Let's try the idea where we like keep track of the depth of where we're at, right? So let me just write all of the numbers. So we have like 6, a 5, a 4, a 3, a 2, and a 1. And then we also track the nesting level for each number.
Okay.
So would we say that this is nested 2 deep?
Mm-hmm.
This is nested 3 deep.
Mm-hmm.
Is this 4?
No.
Or should 6 be
off by 1 for this? So 6 is in a pair that's nested 1 level.
Okay, so we're basically talking about 6 itself we're talking about the parent of 6. The parent of 6 is a pair that is nested 1 deep, right?
That's correct. Yeah.
Yeah. So this is 2. This is 3. This is 4. This is 4.
And the last one
and
is 0.
is 0. Yes.
Mhm.
So what we would do is, to find anything that's 4 deep, we would just scan this direction until we hit a 4 on the second array. We kind of do this until we hit that 4. And then we know that it's a pair. And let's assume that you're like, this pair is not going to have another pair inside of it, right? That was the question you were asking originally. Is like, can you have something that's 5 deep?
Yeah, and I don't think so.
Okay. So we'll hit a 4, and then what we'll do is we will add 3 to the 4 here, right?
Mhm.
And then this 4 will become a 7. This becomes a 7. And then we will add the 2 to the 1, right?
Mhm.
And that becomes 3, right?
Mhm.
And then we collapse these two. And so this is the tricky part, right? We have to collapse both of these arrays that are tracking our data.
Mhm. And that gets replaced with the number 0 at depth 3.
And so reconstructing the pair here might be the challenging part, right? So what are we after?
That seems hard, yeah.
6, 5,
7, 0,
7,
3.
0, 3. This is depth 1, this is depth 2, this is depth 3.
Mhm.
And so the question is, what goes in here, right? What is it being paired with?
It's being paired with 7.
And
it's
how
depth
do
3.
you know what to pair it with? What is the rule that you're using?
That's the hard part, yeah.
Is it that you pick the highest depth value of the neighbors? I don't think that's that simple, right? I think
This is a weird one.
I think you actually have to respect the tree structure, right? So I think this is why the tree is better, because it
Mhm.
makes this particular problem easier.
Yeah, I think we could come up with an even more complex counterexample that would make this sort of not, we'd lose too much information in this particular structure.
Yeah, you could imagine a situation where this was 1, 2, 2, question mark 3. Sorry, 2 over here. Let me actually make it clear what I'm talking about here.
Mhm.
And there would be a question of, well, do I go here or do I go here, right?
Well, you couldn't go left because the one to the left is already a pair in this data structure. Not that that is particularly meaningful.
Oh, yeah. I mean, the problem is the example I gave is impossible, right? Like, it's not actually logical, but
Yeah, right. Weird. It's weird. No, that's not an impossible example, I don't think.
So
it's just a
the other
different
thing we could do is keep
structure.
another array that tells you which index you're paired with, right? So maybe let's go back to the original example. We had 6, 5, 4, 3, 2, 1. And then we had a depth value. This was 1, 2, 3, 4, 4, 0, right? We could also just like indicate who you're paired with. Well, it's hard to know because you could be paired with another pair, and the pairs aren't represented here. That's the fundamental problem that we're talking about, right? It's like we don't have pair relationships.
I think the tree makes the most sense to me. I think we should sort of just lean into that.
Okay, we lean into the tree. Very good.
Yeah.
All right, so let's go back to the tree. It's a little bit decorated right now, but the question that we had with the tree was, how do we find like the character that's immediately to the left of you?
Well, if you I guess we have to step up and know that we came from the right. Oh, and then, right, because if, trying to figure out, like, could there be another pair at 4? And the answer, I think, is maybe.
There can be, but I think what we do is we say phase 1 of our step up is to do this maneuver. And then we call a depth first search here. And if nothing comes out of that, then we do this maneuver.
Yeah.
Right.
Yep. Because we're looking for regular number. So we're looking for the first non-paired number. I think
in tree language, it's a leaf. Yeah.
I think right. And I think the maneuver going from the pair up and back down to the node 4, that always has to resolve. There's always a leaf there if we're doing depth first. We'll never not hit a leaf, right? That would be very strange.
Unless we're at the unless we have a structure that looks like this. Let's make another like if we had a structure that looks like this.
Yeah. Mm-hmm.
1, 2. So this is depth 0, depth 1, depth 2, depth 3, depth 4, right?
Yeah, I was gonna say that's not a valid. Everything has to have a pair where it's a full tree. Yeah.
So in this case, we're nested 4 deep. Or maybe I think I might be missing a level, right? 1, 2, 3, 4. It's the parent that needs to be 4 deep. So I need to add one more level there. This is getting messy. Let me write a different tree.
Oh yeah, I guess what I see what you're saying though, because like as you go up that edge, if you never find anything in that direction, then yes, there won't be a leaf. Yeah. But that's our 0th case where we just drop it entirely.
So in this case,
A is just gone from the tree. Yeah.
Yeah, you got to go up.
Yep. Okay.
And if you know you came from the left, then you need to go up again. And if you know you came from the left, you need to go up again. It's only until you can do this maneuver, right? Where you can go where you're coming from the right. So does that mean that each node needs to know not only it needs to point at its parent, it also needs to know what child it is, like I remember the left child or the right child?
I think so. Yeah.
Okay. I think I have a loose idea of how to do that. I think it might become a little bit more clear when we actually write the code, right?
Yeah, let's throw this into a little code. I think we're close to being able to sort of abstract this.
Okay, and then split. I'm just trying to remember what this was. To split a regular number, replace it with a pair. The left element down the pair should be a regular number divided by 2 and rounded down, while the right element of the pair should become. Oh, is this how we could get 5 deep?
No, well, maybe, but you always explode first. So I think you would find every pair that's 4 deep and explode them. And you as soon as you're going through this action list, if you hit explode, you start again at the top and explode again. So I think you'll do all your explosions.
Oh, I see. You can only do one action.
Yeah. So you have to handle all your 4 deep, and then you split and you generate new 4 deeps that need to be exploded again.
Oh, okay. So you can't actually do like, I'm going to process this until I can't anymore, and then process this until I can't anymore. Okay. So I was wrong before. What I said was actually the opposite. Yeah.
Once you split, you have to check for explosions immediately after a single split action, not process all the splits.
Oh, I see what you're saying. Yeah, totally. Okay.
Yeah, so no depth 5. We'll never be able to get it, which is good.
Okay. So let's go ahead and lay down some code.
Sweet.
Where I put this other
device. Should we get our data too? What's our data? They're gonna give us a wild number. Of the iPad rotating.
Yeah, the input's going to be kind of nasty. What is so these are actually multiple numbers, right? And they are asking us
add them. Yeah.
Oh, we're supposed to basically reduce every single number, or we're supposed to add all the numbers together. Is that correct?
Yes, we're supposed to we take the numbers and add them in sequence.
And then reduce them in sequence as well.
And then add the next one. Yeah.
Okay.
So I think it's take the first number, take the second number, add them, reduce them, add the third number. Yeah.
Okay. Rather than work with our real input right now, I think I want to just run the explode rule through some examples and see what we can go from there. Okay, so tree problems famously difficult in Rust because
Like that.
we want to have mutable circular pointers, right? Like if you're traversing this tree, you're going to want to modify it, which means you want mutable pointers everywhere. We need a pointer from parent to child, and we need a pointer from child to parent. And I think there might be an issue with having circular mutable pointers. Like the classic thing you can't do in Rust is the doubly linked list, unless you be a little bit clever about it. One thing we can do, though, is essentially invent our own memory model, which is to say we have an array that represents all the nodes. Okay. And then the pointers are just actually indices into that array. Okay. So every time we do an operation, we're passing in the full array of nodes and then like indices that imply, like basically point at what we're talking about. And therefore we essentially have global access to modify the entire tree for every single operation that we're talking about, rather than doing it in what I would call an object-oriented way, where we're just like focusing on one node and we have like mutable pointers to each one. Does that make sense?
Yes.
So that's going to add some complexity. I'm going to ask you to kind of like just roll with me and see how this works. And if it starts to get untenable, we can try to model it in a more traditional way. We can even use unsafe if we want. An unsafe means that we just get like a raw freaking pointer that we can use to modify stuff. Does no borrow checking or anything like that.
Now let's see what we get. This is, it's weird. This is like an order of magnitude harder than the last couple problems.
This is the hardest problem that we've had so far, I think.
Yeah.
We could be complicating it, but I think that but I haven't seen the trick yet, as it were. Mm-hmm. 1 second. Okay. Well, let's get rolling. I do want to just be able to parse something, right? Let's pop this back up. So let's even just talk about parsing, right? Because that's going to be interesting to do. And then like our representation of this is going to be a vector of nodes, and maybe is the root always going to be the front node in that vector?
Always the front node.
Let's just call this the struct tree. And it is going to be like vec node. And some indicator of where this is. And then we need to actually talk about what a node is. And a node is either a pair, which has 2 nodes in it, or it's a leaf, which just has an int in it, an I32, right? Node has infinite size. Okay, so it's complaining that like our node, like if we try to put a node inside another node, it could expand to. These aren't pointers; these are actual values, and so it doesn't really have a way of expanding this notion of an enum, because a node can be a pair. That means that this could be a node of a node in here. And because this one could be a pair, this could be a node of a node. And because this could be a pair, it could be a node of a node. Right, so basically this is like infinitely sized. Think of this as like a C struct and not a heap allocated thing. So we would have to box these and make them pointers. So the way that we do that is it's a tuple of a box of a node and a box of a node. And a box is just like a heap allocated pointer, right?
And it's happening.
So
Cool.
we were also saying though that like we need to know what our parent is, right? And we also need to know what direction we're coming from. Does that seem right to you?
Yeah. Right, the pair of node, does that actually need to be a struct of like keys left and right?
Yeah, so let's try that. So we have like a leaf node, and the leaf node has some common stuff, right? It has like our parent, which is a U size. It's like an index. And then we have enum child left, child right. This I'm going to go ahead and just like do my boilerplate derive, debug, clone and copy. We want to treat these as values basically. And I think these are going to be optional, right? Because we might be in the root. So you see how complicated this gets in Rust, right? And then we're going to have a value.
A leaf will never be, it might not have a parent. It will always have a left or rightness of it.
Right. So maybe we have a struct parent data. Which is this.
Mm-hmm.
And then the parent of a leaf node is a option of parent data and a value, which is an I64.
Okay.
The pair node is going to also have this. And then it will have a left child, which is a U size, and a right child, which is a U size. Does that look right so far?
I think so.
Okay.
This is really throwing me for a loop.
Yeah, it's tricky, right? And then a node can be a leaf, which is a leaf node, and a pair, which is a pair node.
Hmm.
I think we can do this. This is just complain that we never construct it. Yeah. And this we can also, we probably don't want to copy it though. Okay, so we could actually just create a tree and then like artificially, and then like rather than worry about parsing right now, we could try to run the explode operation on it. Does that make sense?
Yeah, I think that'd be helpful. Yeah. I like that we have test cases for both explode and split, so we can maybe we might want a quick parser and or unparser to see if we're matching, but I think we can verify this by hand. Yeah. Oof. I see what you're saying.
So let's actually put together a tree.
Harder.
Yeah, it's a lot harder, right? Let's actually put together a tree right now. It's a tree, and we're going to have a vector of nodes, right? And which example, should we just use the example that we were looking at before?
Yeah, the 654321 is pretty good.
So I'm just going to go left to right, really, right? The parsing is going to be difficult, right? Now that I'm looking at it. So the first node is what? The first node is a pair. How do I do this? It is a node.node pair of
some pair and one.
the parent is a none,
Mhm.
and the left child. Oh, geez, how are we going to parse this? This is going to be challenging.
Mhm.
Left child, I think, is just index 1. The right child is index 2. Let's keep on going, right?
Okay. Yep. Yep.
What is the left child of 6? Let me see if I can bring this up. Oh, God. Did I redraw this tree somewhere?
I thought it is that one. Oops.
Okay, it's a little bit hard to read, but bear with me here.
Mhm.
The left child, so the first child is this pair, right? The first node is this pair. Or should the first node actually be this pair?
That is the first node in the tree, I think.
That's the root.
Yeah.
Okay, so then the first child of this is going to be array index 1. This is going to be array index 2, right? So we're doing essentially a breadth first traversal of this.
Oh, I see. Yep. Okay.
Although I don't know how we breadth first traverse something that we parse, because we parse this essentially like leaf-wise, right?
Should we, is constructing this by hand useful versus should we do a,
Do you want to actually parse it?
yeah, or should we like do some construction where it's like, at least it goes through and it's like, it adds a child node with a pointer to the parent instead of us having to try to construct it out of one call. I think
Sure.
writing the structure by hand looks a lot harder than parsing it at this point.
Okay. Let's try and parse it then.
Okay. Man.
I don't know how amenable this data structure is to immediate parsing, right? The other thing that we could do is use runtime. So you can do
into an array somehow, yeah.
So you can you can do you actually can do point like nodes that point at each other mutably using a thing called a ref cell, which needs to then be basically what it is like at runtime, what it'll do is it's a data structure that allows you to pull a mutable pointer to data off of an immutable object. But before it does that, it does like a lock. It does like a mutex lock around it. The whole point of this is to make sure that if you have multiple threads pointing at something, it does like it allows you to make sure that it enforces all these borrow checking rules at runtime rather than statically. Does that make sense?
Makes sense why it's there. Yeah. Oh, okay. Do you think they designed these problems to be hard for certain languages?
No, we're trying to do something that's like relatively simple in most languages, right? If this is JavaScript, to be relatively easy, I think. Well, okay, let's even just imagine that we're trying to parse this in JavaScript, right? What would you do?
I guess.
I think as soon as you would like see an open bracket, you'd say, okay, create a new node, right?
Yep.
And then as soon as you saw a new open bracket, you'd say create a new node and make that the left child of the previous node that we're on, right? We would keep a stack.
I mean, would you ever parse it from two sides too? Would you pop off the bracket on the left? See that it's.
I think you might do a recursive maybe we do this recursively, right? Like we'd say, okay, as soon as we see an open bracket, we'd say, okay, parse a left tree, and we'll get a node out of that. And then at this point, I'm expecting a comma. Then parse the right side of that and get a subtree out of that. And then I'd be expecting a close bracket. I think that's how we would do it, right? Is we would do it recursively. We would say like consume an open bracket. Now just give me a tree. So I call the parse function again. Then I would expect a comma. I would expect a space. Oh, there's no spaces in here. And then I would say like parse the next tree, and that would return something. And then I would expect a close bracket, right? So I guess it would be something like if S starts with bracket, else S dot essentially like consume number literal, right? And what we would want out of this is actually not just the tree, but like the remaining string, right? We want basically like how much of the string did we eat when we parse this tree, right? Does that make sense? Because what we would do is we would say like let rest, like let subtree rest equals parse of S. And we would call this like the left subtree. S dot consume comma. Let right subtree rest equals parse rest. S dot consume left bracket. Return my like tree with like left subtree, right subtree, and rest. Right, that's like roughly what the algorithm would look like. This is pseudocode I'm writing here, but this is kind of like what it would look like. And here we return like, I guess this would be like a pair node. And we do S again, because I'm assuming like S gets mutated, but or maybe this consume number literal is more like this. And then we pass the rest back.
Okay.
Does that vaguely seem like the right? This is like how you do it in like any other language, right?
Yeah, I'm confused by the rest part of it. How would you consume the right subtree and have anything left over?
Yeah. So one example is like, let's say you were here, right? Let's say you're just like consuming. You're trying to like parse this. And then what you'd have the remainder of, you like the string that of input is like this whole thing here, right? You get to this open bracket, and then you like need to say like, okay, I'm gonna parse the first thing, which is this. I get a 4 back, then I eat the comma, right? And now I want to consume the rest of this, but get one. I want to get one tree out of it, right, or one node out of it. Because this only has one open bracket, it's going to stop at this closed bracket, right? And then at that level, it would return over here. But you still need to know what the rest of the stuff is, right?
I see. That's very clever.
Yeah.
Huh. Cool. Yeah, that makes sense then.
Okay. What we can do at least is actually we can do this and make it not mutable, and maybe we can worry about dealing with the Rust aspect of it next. How does that sound to you? Because it's the mutability that I think is
good.
like we're trying to work around right now.
Yeah.
Okay,
Yeah, this
so
is the most underwater I felt in Rust so far. Sorry.
say one more time.
Oh, it's just the most underwater I felt in Rust so far. I'm sorry.
I'm feeling right behind you, so it's okay. So if we were to do this instead, I think what we would be looking at is we'd have essentially a tree data structure, which can either be a pair, which has a pointer to a tree and a pointer to a tree. Let's not worry about the reverse pointers for now. Or we have like a leaf, which is an I64 value, right?
I do have a dumb question. Is there any reason not to use like eval here and let that do its job? I feel like we're about to write that algorithm basically.
When you say eval,
we might have to convert this to sort of the like what is an array literal in Rust? Is it array open bracket or is it curly braces here?
oh, I see what you're saying. Array literals, these would be vectors because you don't know what their length is until you actually parse it, right?
Oh,
so
true.
like a literal vector looks like this.
Mhm. If you nest it, it would just be another one of those in there.
Yeah, and I don't think the Rust evaluator is like in the standard library. You can probably pull it in.
Oh,
I mean, we could actually pull in a JSON evaluate, like a JSON deserializer, because this is valid JSON, is it not?
Oh, yeah, that's a good point. Okay.
We could do JSON. Like, I mean, that might save us from having to do the parsing.
What's your rule on crates so far? Have you used any? Because I don't want to. I don't want to break.
I kind of want to write this just because I think it would be educational.
I think you just put the correct algorithm together. So let's do it.
Okay.
I forgot that the language doesn't actually have that built in.
Right. Okay. So what we actually need to do is like we need an interface for string that allows us to do this like consume comma stuff. So maybe we can do this like consume comma or consume character, right? And it's like S, which is a string, and then a C, which is the character, and it returns another string reference, right? And so what we want is if like basically if S dot starts with, can we do starts with a character? Yes, we can. So we're just going to assert that S starts with that character, right? And then we're just going to return S. How do I slice a string? I forget. Like, is it like this?
That's what I would have guessed for it.
Ampersand? Yeah. Okay, cool. So that's consuming a character. And then we want to do consume number literal from the front of a string, which I think is a little bit harder. And then we're going to return an I64 in the string, right? And so here, I think what we'll do is we'll build up a vector of characters, right? And so for
every number is single digit for what it's worth. Is that
every number is single digit? Okay, that actually helps, right? So we don't need to do this like parsing really, right? We're just going to basically say
in our input, at least in our output, that's not true, but we don't have to worry about that because we'll have our data structure. Yeah.
So we're going to let the character equal the 0th character here. How do I get the first character? Maybe I'll just do chars. And we'll assert that C is something and C dot unwrap dot how do we say is ASCII digit? Is digit with a radix of 10.
Nice.
I think I'm just overriding C. Actually, we're just going to do like C 2-digit, right? I could just be unwrapping here. These assertions are maybe a little bit pedantic.
Yeah, we've been pretty flippant with assuming that we won't get bad data like that in the past. So let's just go for it. And then string sliced 1, yeah.
2-digit is a U32. Let's just make these U32s for now. I don't want to fight the type checker at this point. So what we'll do here is we'll do let rest equals consume comma, consume character of rest and a comma. Rest and a closing bracket.
Right bracket, yeah.
And then I think we need to consume the first one, right?
I think so, yeah, because we never got it out of there.
And
the first one is consume string, not rest, and then you're good.
Should I just be using S the entire time? And this is a tree. This is a pair, which is a box.new of the left subtree and a box new of the right subtree. What box does is it essentially just creates a pointer, right? It moves this value onto the heap and then returns like a structure that goes around that says, I actually have an internal pointer to the heap for this, right? And if the box itself goes out of scope, it'll take the value off the heap. You can only have one box around one value. If I wanted to have multiple, we have to move it into a ref cell with reference counting, right? So you can do like Mac OS style reference counting. You just have to like explicitly like stick it into a structure that does that for you.
Weird. Okay.
And then we return S with that. So let num S equals consume number literal of S. And then this is like a tree leaf of num, right? And then we return S with that, along with that. And leaf is a U32.
Yep.
Okay, let's go ahead and just like derive
Holy shit.
debug and clone of this. And we can actually just see what this is going to do if we attempt to parse something, right? So we could just say debug of parse this string right here, right?
I'm really curious. Okay.
Get input is never used. That's fine. So we'll see what fresh hell comes out of this. Make 18A. Oh, day 18A. It's building. Took a while to build. Okay. So we have a pair of a leaf with 6. I guess we want this diagram now.
That actually worked. That's wild.
6, 5, 4, 3,
3, 2.
2, and then 1 way at the top, right? And then returns nothing at the end, which is what we wanted, right? Okay, so I think that kind of worked, right?
It did.
Yeah.
I'm impressed. How do we need to keep track of parents as we're building this?
We probably do. We can try to write the explode function on this structure, and then we're going to go like, oh shit, we don't have the right references to stuff, right? And then we can maybe go from there.
Okay. Yeah, let's do that.
Okay, so let's say we write an explode function. And it takes a tree, which is a mutable pointer to a tree, and it returns.
I was talking to a microphone on the other side of the room. Sorry.
And it returns a mutable pointer to a tree, which could just be the same tree again, right? What a tree, if you ever call explode on a tree, it's never going to modify the root of the tree. Is that correct?
By the root, do you mean the root pair? Because it could, the pair that's at the right or leftmost node on the root pair could be modified.
Would it ever convert a root pair into a? Would it ever convert a root pair? It's always a pair. It's always going to pair. Okay, so we could actually not return anything, and this we would know is a
pair, yeah.
We could actually just do a mutable box. Let's do a mutable tree, right? And then we would match on the tree type. And if it's a leaf of anything, we would just evaluate to the tree itself, right? And be done with it. But if it's a pair, if it's a tree pair, sorry, I have to prefix these. Tree pair of left and right. We got to do some shit, right? Oh, no, we need a semicolon here. Yep.
Should explode, I wonder if this is another recursive function. Should explode just keep track of the depth that we're at? Because if we pop back up.
Can I do I don't think there's default arguments in Rust, which is kind of crazy to me.
Oh, that's too bad. Surprising.
Yeah. Okay. So we've got left and right, right?
I guess if.
So the question is, how do if I have a mutable tree here, the thing that's mutable is this tuple, but is there a way I could do something like tree equals left, right? Is that valid code?
Expected enum tree.
Like this is just like replacing it with itself, right?
Huh. It's not happy with the mutability of that.
Yeah, and so this is where we kind of get into a little bit of the difficulty of like what it's complaining about is we already have like a mutable pointer to these things, and we're trying to create a second mutable pointer to those things. Although technically we are deconstructing the original thing. So what we could do is we could take ownership of the tree and return a tree, right? Essentially, we're doing functional programming now. We're basically saying this function just like actually takes over the entire piece of memory that this tree represents. And then it's going to return an entirely new thing. So in this case, we would actually just return the tree back if it's a leaf, or we would just return this, right? If we were just like trivially reconstructing the tree. Does this make sense to you?
That's right.
Okay.
Yeah, and then if you run explode, you should get the same tree back out. Yep. Okay, so I guess.
Yeah,
I'm thinking it through our depth check there, like for the pair match clause.
Yep.
If the depth is 4, we do a thing. Else we explode the left and right, or we attempt exploding. Is that right? Like we add 1 to the depth and call explode on both those nodes and return that.
Yes, exactly.
Yeah. Okay.
But we only want to do it once, right? So if there was like a 4 deep on the left side and a 4 deep on the right side, we wouldn't want to do it on the right side. Yeah.
Ooh.
So does that mean that the explode needs to return like whether or not it actually operated on the tree or not? Like I actually exploded it.
I think it will need to, yeah.
Something like that. So what you were saying is like if depth is equal to 4, do the actual explode thing. Otherwise, we'll do an early return there, right? Otherwise, we are going to say let left equals explode.
Explode left depth plus 1. And do we need to pass exploded all the way through this too?
Can you say that one more time?
Do we need to pass the Boolean to know that we've operated on the tree or not all the way through this?
Yes, we do. So like if done, we return, or let's call this exploded, right? Exploded. We would return a new tree that is a pair that has the new left, the old right, and true, right? Otherwise, we say let right exploded equals explode right depth plus 1. And if we exploded, I think here we can just return tree pair of left and right exploded.
Yes.
And it is complaining here because this is a box. Oh, but left is a tree. We need to like, we basically need to rebox it here. Yeah, right. And then I think we need to unbox it here. So how do we do that? To owned. What if we just pass a pointer? Yeah. Pass a pointer here. Yeah, so you can see how we're getting into like some kind of crazy complexity with Rust here, right?
Sure am. Wow.
Yeah. All right, so what's it complaining about here? Tree bool. Isn't that what we're returning?
Not on line 52, I guess.
Okay, so if we were actually doing the explode thing, this is where it gets really complicated. Okay. Maybe explode actually needs to be broken down into a couple of steps, right? Because if we're at depth 4, we've already lost. We're like our only context in depth 4 is this right here.
That's right. Yeah.
So what we're actually doing is we're replacing this with 0, are we not?
That's, yeah. So we replace ourselves with 0, and we're you basically returned 3 and 2 up the tree as left or right addition.
Correct.
I like how that works recursively. It's a funky return type that we got to work with, but at least it's pretty clean.
And then,
so interesting thing. Can you go back to the code real quick?
yep.
So
this could be an option. Instead of a Boolean, we return like an option of the exploded value. Is that what you're saying?
The exploded values, yeah. Or if it's the pair, right? The tree leaf on 52 is interesting because if we have, I think that's where we need to know if we are in the process of exploding, that we will choose to add to the leaf node that we're on if it's a left node and there's a left value to consume. Does that make sense?
We might be able to take care of that. Yeah, I see what you're saying. We might be able to take care of that if we call explode and it returns that we just actually exploded a pair. We might be able to take care of that addition here. But we would need to like pass down a value. It would be a different function that we would be calling basically. Boy, this is really complicated, isn't it?
It's gnarly as hell, yeah.
Yeah. Well, I mean, how would you do this even if you could mutate the tree, right? Like this is actually a problem in, like if this is the JavaScript version of this would be equally challenging, right?
Yeah, it's
the JavaScript version. Maybe you would do like find me the. I think what we would do in JavaScript is rather than returning the tree, we would say like we'd have the reverse pointers back up to the parent, right? We'd say like, okay, we now have the reverse pointer going up to the parent. So once we like in our function, we would call. Actually, I don't know if it's that much easier in JavaScript, to be honest, right? Because you still have to do this like recursive going up the tree, right?
This is a hard problem in any language, yeah.
Yeah. It's tricky, right?
When if we got down to that node and started going back up, we'd have already actually handled the branch to 4 on the left as a leaf node, and we actually couldn't expect to recursively reprocess that. It's really annoying.
It's just different stages, right? So like this explode is really explode stage 1, like start explode. And then like maybe I'll even just call it that, right? Just to if we call start explode here, if we exploded, I think there's actually 2 different notions of done here, which is really, really complicated, right? There's almost like an enum of results. One result is that we fully handle the explode in the child and we're just totally done. Right? And then we can just percolate back up, which is essentially what we've described here. The other example is that we have somehow, we've done an explode in the child somewhere, but we still have this like number 3 and number 2 floating around, and we need to actually still handle those, right?
Yeah. Would it make sense to find the node that's about to explode?
Yeah.
Replace it with 0 and return the tree and return a pointer to 0 so that we can then, would it help for us to be able to keep track of, if we had parent pointers and we were replacing that one thing, then we could modify the tree, get a tree back with 0 that has a correct parent pointer, and then jump into that node and walk up the tree with the 2 values that we're going to replace on left and right. So like basically we're recursing down, finding our exploding node, updating the tree, and then basically we're saying it's 2 steps. Did what I just say? I'm not sure it made any sense.
It does.
So we do need parent pointers for that.
Yeah. I'm going to try to figure out a way to do this without parent pointers. Let's spend the next 10 minutes doing that. And if that gets complicated, we
Okay.
can try to add the parent, because the parent pointers just add like another layer of like, shit, got to add like the box ref count thing. And it gets a little bit confusing in Rust. So I think what I'm going to try to do is like, I'm going to make an enum that's called like explode result.
Okay.
And there's just like one that we're just completely like exploded. And then we have like we still need to like merge, right? We still need like, there's basically like two things where we could potentially need to like merge in. So it's like must add. And that's like a pair of optional values. God, this is complicated.
What case would there be that there's only a left or right?
I don't know yet, but let's
Okay.
try and figure this out. So a tree here, so the Boolean here becomes an explode result, right? And for leaf case, you did nothing, right? Okay, so if we explode left here, we need to match on the explode result. Let's just call this res. And explode result, nothing, means you need to continue down the right branch, right? And if we did explode results, exploded, we're done, right? We should not explode down the right branch. We're basically this. Oh God. Oh, and then if nothing happened, we need to do the right side, right? Because nothing happened, we need to actually continue to like try to explode the right side. Is that right?
Yeah, that's where the right branch happens. Yes.
Okay, and then so how do I prevent like this from like infinitely recurring? Because then like I need to add this match branch. I need to add a version of this match handling the result of the right side, right? This is when like we exploded the left side. You see what I'm saying? Like, how do I avoid doing this like down here? I could copy all of this stuff and put it in here. Only this is like the right side. The right side, right? So how do I avoid doing that?
Real good question. Damn.
I could write a function that handles these two. Let's just expand this, and let's just assume that something goes in here, right? Do the same on the right. Okay.
Okay.
We'll solve that problem later. I'm going to get rid of all this stuff. If we actually did explode, I'm going to actually put a dummy value in here just so we don't get this like noise. This is a to do. We don't want to box the box. Same thing here. Okay. I think this result is actually correct here. Like in the case that we exploded something in the left and like everything was like fully resolved in that subtree, then we're done, right? Now we have, I think maybe this case is the one that we would get if we're like at the depth 4. Right? So if we're in depth 4, when do we explode? We just explode here, right? So we would return
every time, yeah.
We'd have to actually return like the null tree, right? Or nothing. Does the result tree need to be part of the result?
We return a leaf node of value 0.
Oh, you're right. Okay. So we return we'd return a tree leaf node of value 0.
And
explode results of must add left right. And this would be, we'd actually have to pull the values out of our left and right here, right? So we would assert that the left is
it's weird, but they have to be, but yeah.
Equals left. Oh, I think we can do something funky like this. Let's match left and right and dereference them.
Okay.
And we can have a tree leaf left val and a tree leaf right val. This is actually a nice expression in Rust. Return that. Left val, right val. And anything else should be like unreachable, right? We should just not even get to this point. So basically we're saying we're matching against both of these values, like the pair of them, and they both should be leaves. Otherwise, like we've basically got an incomprehensible result, right? Or I could even just do it like panic. Reach depth 4 with invalid node. Tree. Oh, I think we already moved tree, so we have to like reconstruct it. So we need to like actually.
Wait, we're matching on tree. We can't use it here?
Well, we deconstructed it here.
Oh, I see. Yep.
So I think if we just do left to right again. Oh, it's partially borrowed here because we matched against it. Once we dereference, we lose the values. So I think we just do AB and then it's gross, but that'll do it. Yeah. Actually, we can just call this X and just put X here.
And panic. Yeah.
Or I'll call this like. Okay, so now we actually produce the result, but we actually have to handle it here, right? So I think we're actually calling a different function now, right? This is where we actually want to like reconstruct a tree by pushing values down, right? So once we've exploded, right? We've exploded these two. Now we're going to be in the context of this node, right? We're going to basically pop off the stack. And that's where we are in this piece of code right here. We're like right here. And in this case, it happened on the left side, right? So actually, let's draw an example that like actually matches the code that we're writing here. So it's this one here, right? So we have now taken care of, this. This is now 0. And we've passed A and B back up here as stuff that we need to like modify with, right? Because we're, and right now we have done this because we handled we exploded the left child, right? So what do we do now? We can push down B. We can push B down to the right side, right? Like the right value here.
Oh, interesting. Okay. Yeah.
So maybe there's just like a new function that's like push right value down the right side, RV. And that's going to be another like let right side equals that plus, is it done? And then we're going to say if done, then we return a pair of the right. And then this is just like must add just the left value now. This is why I was saying like maybe we want to return just the left side. You were asking why we needed that case, right?
I see. That was a good insight. Yep.
Otherwise, we didn't succeed and we just need to do both again, right? And must add left is like this thing, right? Horrible, right? And this
is quite a thing.
So I think the parent pointer thing like starts to become attractive, right? Because we have to do like a. The thing is like there is a version of this complexity that we have to manage regardless of what we do, right?
Yeah.
Now there is the option of doing this thing again, but we had an issue of just like finding pairs, right? Or like knowing what to merge against.
Yeah, I did not find that to be at least a clear win, though.
Okay.
It's making me wonder, that's for sure. Because it's easy to generate that from the string input. You're counting brackets as you go down.
Yeah. Well, how would we extend this, right? Like if we wanted to know the pairing, I think we were asking. Let me try to redraw this. Let me try to redraw the problem, right? We started off with 6543210, right? And we also knew the depths. These were 4, right? This was 3, this is 2, this is 1, and this is 1. Was that how we did it?
I think on the left the depth is 0, or on the right the depth is 0, but otherwise yes.
Right. So what is a good way of representing pair relationships here? Like let me actually write the indices.
Could we do
here. So this is index
I was
one.
gonna say,
index
would
two,
a hash
index
map of index to paired index be useful? Like if we want to look up the pair for index 3, we have a map.
Yeah,
of 3
we could
to 4,
totally do that. And let me just like
3.
render the hash map on this line. I'll render it like horizontally rather than vertically.
Yeah. Mm-hmm.
So the pair for this one is index 4. The pair for this one is index 3.
Mm-hmm.
The tricky thing is like the pair for this one is actually another pair, right? The pair for this leaf. And so what's tricky is we're materializing the leaves here. And damn,
yeah.
And why does this matter? It's because we're trying to figure out what to pair the 0 with, right? When we replace 3 and 4 with 0, where does that merge to, right?
Yeah.
Does it just merge to the closest 3? And the problem with that,
that's the constraint I'm trying to figure out if it's real. Is closeness real in this representation?
It's not the closest 3 as well, right? I think I can think of cases where it's not. It could be one that's farther away, right?
That's what I'm thinking.
Because the 3 to the closest 3 is just the leaf node that appears nearest you, but like it could be like a bunch of levels deeper than where you currently are, right?
Mm-hmm.
Wait, is that true? I think you need to merge with a 3 that's near you, like a level 3 near you. And because this is the leftmost, you're always guaranteed that there's going to be a 3 either immediately to your left or a 3 immediately to your right. Does that make sense?
It's either there or it's nothing. Is that the constraint?
Well, we're only ever looking at the leftmost 4, right? And you're guaranteed that there's no other 4s before you, right?
Mm-hmm.
So either there's going to be a 3 next to you on the left side, or there's going to be a 3 next to you on the right side.
Yep. Right. That has to be true for at least one side of this thing, since we are nested in a pair. And at depth 4, nothing else can be at depth 4 because we are a previous split that we are handling as an explosion. So yes. Oh no, because when we add numbers, we do the weird addition operation could put stuff in.
Hey Dom, does it matter who you pair with? It doesn't matter who you pair with.
Doesn't matter who you pair with. That's a good question.
Like, do we ever change the ordering of? Will we ever radically reorder the numbers by exploding? Or do we just become this? Sorry. 7, 0, 3. And then it would be 1, 2, 3, 3, 0. Like, doesn't matter that we're preserving pair relationships.
That's a good question. Should we try?
I'm going to bet that it doesn't matter.
Do you want to run this on another example that they gave us and see what we're doing? Because I feel like you must be right.
Okay.
This problem is so obnoxiously hard if that's not the case.
I think the fact that we're trying to do it in Rust also makes it harder. I'm going to go ahead and comment out this stuff.
Yeah, but the question of how you do this in JavaScript remains pretty hard too.
It remains hard. Yeah. Okay. I'm going to keep the tree here. I think the tree is fine because what it'll allow us to do is we'll parse, and then I think this will make it easier for us to actually just like make arrays. Like, array tree. and it's going to take
Because
what exactly is this? This is a breadth first traversal or depth first traversal?
Going left or right should be.
I think it's depth first, right?
Yeah. It should be depth first because, well, I don't know. Once you get down to depth 4, it's hard to say, but.
Okay. So we're going to take a tree, which is a reference to a tree that we're not modifying. And then we're also going to take a mutable, like a values, which is a vector of U32s, and depths, which is a vector of U32s. And then we also have a depth. Bear with me here.
Okay.
And these vectors are going to be mutable. Okay, so let's pass in the root of the tree. And we're going to match on the tree, right? If we match the tree and we get a tree pair, we're going to do something. And then we're going to, if we get a tree, it's going to complain. If it's a tree leaf, we're going to have a value, right? And we are just, at this point, going to append the value we are going to append the depth. And then go on with our happy lives, right? For left and right, we are going to do, in a depth first left biasing traversal, we're going to make a array tree of t, depth +1. Actually, it's not t, it's left, right?
Left, yep.
And then right. Is that correct?
Mm-hmm.
And I don't know how to get this to behave, but I think that's it, right? And so let's try it, right?
Mm-hmm.
And we can bundle vals and depths into like another structure. It doesn't matter for now, right? So let's just print out, make array tree t. What's our first depth? Is it 0? I don't know, actually.
0, I think, yeah.
What is it complaining about? I need to pass the reference to this. Mutable reference.
T is a tree string pair. So I think we need to get the first component of it.
Oh, yes. Okay, I think that compiles. Let's run it.
Oh, boy.
By the way, thank you for suffering through this problem with me. I know I'm insisting on doing it kind of on like hard mode. Not normally a hard mode video game player, but I'm a hard mode admin of Coder.
That's true.
Oh, you know what? The return value is not doing anything because we're not returning anything. What we want to do is print out vals
and depths. Yeah.
Depths. Actually, what I'm going to do is I'm going to print len with a new line, so it'll look like what we were writing before, I think.
Mm-hmm. And yeah, this sure is a hard mode one, but this is good. It's not how I would have attacked the problem, so I appreciate
6,
it.
5, 4, 3, 2, 1.
1.
2, 3, 4, 5, 5, 1.
We're just off by 1 for the whole depths.
We're off by 1. I would have assumed we were off by 1 in the other direction, which is interesting.
We start at 0. it's because we started this pair at 0, and then to look at one on the right side, we have to have gone depth 1. We don't start at a leaf, we start at a pair. We go from 0 plus 1.
So that's what we wanted, I think. Right. Okay. So this function looks sound, right? So let's do explode again, but this time we have vals and depths. Should I bundle that into one structure?
No, let's just keep them as two arrays right now.
Okay.
Easy later.
Vec U32 depths. And this no longer needs to be recursive. What we're going to do is we're going to find the first 4, right? For D in depths dot iter dot enumerate. This is an I in a depth. If depth is equal to 4, it's not equal to 4, we just continue, right? If it is equal to 4, then we have found our pair, right? And we're assuming that the problem is structured that we're not going to have pairs at depth 4. We're only going to have leaves at 4, right? Oh wait, we don't even care about leaves anymore. We just know the value, right?
It doesn't come up in that respect.
So what we do if we get this far is if I is greater than 0, then vals I minus 1 is plus equal vals at I. Is that right? If I plus 2 how do we know if the right neighbor exists or not? The right neighbor is at index I plus 1, right? The right value is I plus 1. So we need to make sure that this is less than vals dot length minus 1.
I think we can confidently say I plus 1 exists.
What if we reach
found the left
end
half of a pair at 4? Well, if we found the left half of a pair at
I'm actually trying to say does this exist? Does the 1 exist?
Exactly. So I think you're back to I plus 2. I plus 2 is the right choice for that.
If I plus 1 plus 2 is less than vals length minus 1. Okay, yes. Then vals I plus 2 is plus equals vals I plus 1.
Yeah.
Is that right? Do you think this is a little bit easier to read? I know that's a little bit like extra, but basically we're saying left neighbor is I minus 1.
I like that better, yeah.
And it's basically parallel here, right? And this is like the first. And this is less than or equal to, is that right? If I plus 2,
if you have a minus 1 equals 2 is correct. Yeah.
Okay. I mean, the other thing we could do is this. It's always kind of tricky. If we're trying to be like parallel and we want to use greater than or equal here, less than or equal here, maybe makes a certain amount of sense. Because vals.length minus 1 is the last valid index. And we're trying to say, is the right neighbor a valid index, right?
Yep.
Sorry, this is like so micro. It's such like a micro code style thing, but it's just
All
interesting.
good.
Yeah. Comparison is useless due to type limits.
What?
Oh, I-1 cannot. Oh, I is a U size. So we need to actually. Can we do I as I32? I don't know how we.
Weird. I mean, if I think it's just if I not equal to 0, then you can go back, then you go left. So your beautiful system is broken down. I'm sorry, but
Yeah. If I not equals
fine.
0, you can go left. So let's go ahead and simplify this then. Does that make sense?
Okay. Yep.
Val's I is equal to 0. Depth's I is minus equals 1, or is equal to 3 basically, right? And then vals dot remove I plus 1 and depths dot remove I plus 1.
Yep. Except
Where does the immutable borrow happen? Oh, we're iterating over it.
oh.
Okay, so we just need a for loop here. For I in 0 dot dot depths dot length. Let depth equal depths I.
Doesn't oh, I guess actually we break out of the loop immediately if we hit this case. So
And then we break here, right?
We can't continue. Yeah.
Yeah, we can't continue.
Great. Okay.
How would you structure this normally if you're doing a for loop? Would you say, would I do if depth equals 4, put all this stuff in there and then break? Or is the structure
your nest less code or fewer nestings setup? So
and I like that in general. The only thing I don't like is when like the unnested part of the internals of the for loop end with a break. It always feels a little bit weird to me for some reason. I always think of breaks as the edge case, right?
Yeah.
Okay, so let's explode this. Yeah. So let's just explode mute vals and mute depths. I think it's just going to work, right?
It is. Let's grab a different case.
Okay.
We should be able to turn anything into the correct output from the single explosion example now.
Okay.
So
should we just do all the explosion examples?
Yeah. Let's start with the top one. So we should lose. Yeah. Fuck yeah.
Okay. So it becomes 09234. 09234. And 09 is nested at 3. 234210. That's depth 2, that's depth 1, that's depth 0. Okay. That makes sense so far.
I'm digging it. Okay.
Did we do this one already?
Nope.
The result is 76570. 76570. Okay, so far so good. This is the one that we did already, this third one.
Yep.
Fourth one.
This is splitting across trees, so the right node jumps to the left node, which I think actually works based on what we've done. Do it.
The result is 3280. 3280. 95432 and 5432.
Goddamn. All right.
And all the depths are being modified correctly, right? The only depth that you change
they look good.
Yeah. So I actually think this is going to work, right? I think
so.
I think this is fine. So the challenge here was ultimately, because we reduced the problem down, it's really just about like double parsing. We parse recursively using something that's easy for us to do here. right? We do this recursive parsing of the input stream. And then we take that intermediate expression and then parse it into this double array thing that we've got, right?
Now, I wonder if there's any point to our tree structure at this level. And maybe we'll see once the addition happens.
Yes, I think you're absolutely right. So what are we actually looking for? What is the final answer?
Dude, we're not even close.
Yeah. Oh, I see. We add up all of the numbers. Is that right? Magnitude of the final. The magnitude of a pair is 3 times the magnitude of its left element plus 2 times the magnitude of its right element. The magnitude of a regular number is just that number.
Oh, man.
Okay, so we need to reconstruct the tree. We need to reconstruct the pairs, right? And this is where we need pair information.
Fuck.
But I think,
yes,
Dom,
but
that we can go backwards
yeah,
from this representation back into
I think so too.
this representation. Okay. Do we want to just do addition first?
Oh, yeah. Let's get our addition going on in here.
Okay. I think addition's easy.
Shit. I think so too. This is wild though.
A is a tree, and B is a tree, and it returns a tree. I think we are just doing tree pair of box A and box new A, sorry. Right. And so maybe we should actually handle our input. Should we take this example?
Might as well.
Yep.
Can we do some of the basic addition stuff just to make, I mean, I guess addition's easy. There's nothing.
Oh, I see what you're saying. Let's just add 2 things together. Yeah, let's is there an addition example? Yeah, here's an addition example of this, right?
And then it explodes, split, explode.
Oh, we haven't done split either, have we?
We haven't, no. Though I think split is pretty easy.
Split, if regular number is 10 or 0, the leftmost, sorry, what is split again?
Split is if it's greater than 10, you increment depth and you do a floor ceiling division by 2 on the number. Split, I think, is actually very easy for the array or for the vowels and depths array.
Okay.
You're basically looking for anything that's 10 or more and insert.
If any regular number is 10 or greater, the leftmost such number splits. The first one is the round down, the second one is the round up. Okay. Do we want to make a split then?
Let's do that. That'll be easy. These jerks, man.
Yeah, where did I put explode? Where? I don't think I need any of this other code. This other code is just like a total distraction at this point.
I think so, yeah.
Yeah. So it's the same thing here, right? What is the cutoff? 10? If it's greater than or equal to 10?
Yep.
In 0 ... vals length. If vals I is less than 10, we continue. And then we're gonna finish here. And so what we're saying here is that we basically say if vals I, let's actually call this V, vals I. A and B is going to be equal to this if statement here. If vals I is even, then A and B is just Sorry,
I was
this
gonna
must
say,
be,
can we do a float divide math.floor, math.ceiling, or is that gonna be
we can,
too
but then we'd have
wonky?
to convert them to floats, right?
Oh, yeah, okay. That is a good point.
Else it's odd, right? So this would be v over 2. This would be v over 2 plus 1.
Mm-hmm.
Yeah. So I think I'm doing that. I think that's what this is, right?
Yeah, you're right. That's fine.
Yeah. And that way we don't have to like typecast into a floating point number.
Yep.
Um,
Yep, I like it.
so we have A and B now. So what we're really saying is that vals I equals A, depths I equals plus equals 1. And then we need to insert a new value, right? So vals dot insert I plus 1
Mm-hmm.
B.
Mm-hmm. And same for depths. Yep.
And then the value here is depths I, just that, right? Because we modified depths I over here, and so we're just inserting that value in there.
Yeah. Yep.
Does that split
right.
look good?
Okay.
Maybe we can test it out
That's what looks good.
to split.
Yeah, let's try it.
They're not actually. I guess we can just like do it, right? Let's just like.
We've got this very nice. I like the process they gave us for the add two numbers and do a split. So maybe we can just run through that. Yeah.
10, 1.
Oh,
So
okay,
we'll do a split here.
Uh-huh.
Did I? Oh, I'm adding spaces. Doesn't know how to deal with that.
Oh, yeah.
What I do?
So where
Is this a gap in our parse?
it shouldn't be. Is it that split is actually incrementing the? Can you grow arrays like this? Is that fine?
I think we can.
Oh, it is consume character, huh?
It is consume character. Assertion fail S starts with C.
On parse 24.
Well, this is good. We found a bug at least.
Yeah.
I wish I knew what character we were on.
Oh, here's the problem. 10. We can't parse things that have greater than single digit numbers in them. Parse doesn't support it.
Yes, of course.
So let's add two things. Let's add.
They technically don't exist, right?
They don't exist. They're not correct numbers for this setup. So
they can only happen if. Yeah, go ahead.
I was gonna say let's step through their examples here. Where's the one where they do the add split or the explode split? Because I think that was pretty good.
So you just want to like do the addition here?
Yeah, let's add this. Let's add the two things. Yep.
Okay, so when we parse, we're gonna get the input finally. And we're gonna map these into individual trees, right? So let trees equals get input dot lines dot map. And I think we just pass in. Let's just do the line here, and then like the line, we do parse of the line dot 0. And let's call this a vector of trees for now. And here we want to basically fold these by adding them, right? So let T, which is our tree, equals trees dot fold, iter dot fold of Give an accumulator. What's the initial value of this? I
Tree
can't
zero.
do fold. I'm just going to do a for loop. Let mute a equal, let sum equals trees 0.
I think so.
And for I in 1 of trees dot length, sum equals add sum to trees of I.
Does not implement the copy trait.
Yeah, we can't, because add consumes the tree, we're not cloning it. We can clone though, or what we can do is we can actually for loop over the lines here. This is what we can do.
Mm-hmm.
Although we need the first one. Here, this is really shitty, but lines.next unwrap. This gives us the first value. We're going to parse it, right?
Mm-hmm. Mm-hmm.
Okay, and then we're going to do for line in lines.
Mm-hmm. You're gonna have to do the same thing where you dot zero. Does that work?
I can do dot zero here as well. Yeah, dot zero is just like give me the first of the tuple. You can think of a tuple in Rust as just like a struct that has like anonymous properties that are named 0, 1, 2, 3, 4. Yeah. And then I need to actually store input because it needs, like, if I'm doing it the way I'm doing it right now, input is like this like ampersand string, like a string slice. And then I get an iterator that refers to it, but there's no variable in scope that is referring to that string slice. So the string slice will actually get destroyed, which means that this iterator is pointing at memory that is like not there anymore. So we do this, and then we can do this. It's a little bit of extra bookkeeping, but I think we've gotten this. And to really just prove it to ourselves, let's just print this out, the sum.
Okay. Cool. Let's see what we got.
So this is after the addition, right? So after the addition, it's a pair that is 4 deep with 4 and 3.
Right, yeah.
I mean, we're really just adding 1 and 1 on the end, right? I think this is correct.
Yep, that's it.
We're not really flexing the muscle of this function or this code here because we're not doing more than 1 addition, right? We're just doing the 1 addition. So I think fine.
So we've got some there. I think the next step is to do a reduce inside that loop. So when every single one we add, we can do a reduction here.
Yeah. Okay. So if we want to do reduce,
just takes a tree or just takes the vowels.
So we need to explode. And if it returns true, then we keep looping, right? Maybe we need a Boolean here, right? Did you do anything or not?
Yeah, did we have an explosion? Because if there is a single explosion, we don't split and we start over.
And so here we're actually returning true. And this is just false otherwise.
False. Yeah. Same for
and
split.
Similar with split.
Yeah.
This is actually kind of cohering together into like a reasonable piece of code. It was hairy at first, but
this went to some weird places.
It did. Okay, so what we're going to do is we're going to loop. And we are going to say if explode vals depths, continue. And then split vals depths. And if we did neither of those, then we're done, right?
If both were false, we are done. Mhm. If not exploded and not split. Not dead split, yeah.
Or just return, right?
Mhm.
Break and return here are the same thing. Maybe I'd like this. This is a little bit more natural. And then just to make sure our language is consistent, let's call this did explode.
Yep, thank you. Much better.
Okay,
Okay.
cool. All right, so now we reduce our sum. This is actually just our tree, right?
I was gonna say that debug sum was good in there, I thought.
Tree?
A true tree.
True tree? You want me to debug the tree?
I think so, because inside the for loop, we should make array tree and then reduce those values. And then we have to retreeify it into sum or into tree. So I think lines 131 to 133 all go inside the for loop. Yeah.
I don't think they need to be retreeified, do they?
They do, because for every addition, we have to do the explode reduce loop or explode split loop, and then retreeify to add the next number to it immediately. Like it's add, and then we're doing.
Oh, so it's add, reduce, add, reduce, add, reduce. Is that the way that this works?
It has to be, because it's not a usable number until it's fully reduced.
It says add the first snailfish number to the second, then add the result to the third, and then add that result to the fourth, and so on. But you're saying it's not addable unless you reduce it first.
The conclusion of addition is reduction. Like you have to reduce after you've added. Because
does that say that in here?
Yeah, it's I think it's earlier in the problem. Yeah, there's only one problem. All snailfish numbers must always be reduced. It's within the first scroll of this.
Okay.
Yep. So right after the addition definition.
Oh yeah, because if we add them all together, you're going to get something that's like really, really deep, right?
Right. We'll be like 50 levels deep, and we depend on it having only a depth of 4.
Okay. Let me just make sure that we wrote the reduce correctly.
Sure.
Okay, so the result of this example down here. 074. 074.
Whoa. Okay. Yep.
786081.
Cool.
And it looks like we are paired correctly as well. Okay, cool. So we need to basically make a tree from values and depths, right? So we need another thing that's
right.
like.
Mm-hmm.
And that returns a tree, right?
Yep.
Okay, so
hear me out here real quick.
Mm-hmm.
Do we need to do this for addition? Because addition is just incrementing the depth of everything by 1 and chaining 2 arrays together.
That's right.
Yeah. So let's just we never reconstitute. At least not yet.
So okay, so what we can do is we can say fn add array tree, and we have avals, which is a mutable thing, and we're basically gonna add into a, right? We don't really care.
Smash onto the left, yeah.
Smash the left. Is that what you're saying?
said smash it into the left, but I would never say smash the left. It's antithetical to my
B
values.
vals, and this is one's going to be immutable, right? B depths. This is where I kind of wish I had just one structure, but it's not that big a deal, honestly. We could make new vectors, make them all immutable if we wanted to. So what you're saying is just like add one to the depth of everything. Oh, this is totally what we should have done in the first place.
And then just line them up. Yeah.
I think avals dot is there append? Yes, this is what we're talking about. So it leaves the other one empty too. It empties the other one. So if we just make them both mutable.
Cute. We are going to have to reconstruct pairs at some point because the magnitude is like a function of pairwise left and rightness, which is funny.
Yes, I totally know what you're talking about. What am I doing? I am like talking out loud and not thinking.
That's cool. Digging it.
And then you're saying we just want to do for like I in a depths at length, a depths plus equals 1.
Equals 1. Yeah.
Brilliant. That is a awesome realization. So really what we're doing is
I wish it would get us, it still doesn't get us pair. I want to get rid of the tree structure entirely.
Okay, but we've made progress, right?
Unless we can.
So what you're saying is we'll do this. Closer. We've got our tree. We make our array tree there. We get our other tree.
We're getting a lot closer to getting rid of trees, so yeah.
Say other tree. This is the other tree. We need to make other vals and other depths. And then we add array tree, vals, depths, other vals, other depths. These all need to be mutable, right?
Oh, yep. It's wild to me that you need to make B mutable to append it, but
yeah, it drains it. Okay. I think there's probably ways of doing that doesn't drain it, but I think it's okay. And then we need to reduce
unexpected
depths. Also mutable. And then this all goes away. This is just this example, right? 074 78 6081 6081. Yeah, okay. This is looking pretty good.
So there's a mid-sized example of input that we can use.
That is this one.
So it's that one. And there's a final sum there for us. So
this is a weird way that they said that they did this. They're saying this is the answer. The input that results in this is this. Is that what they're saying?
The final. That is weird, right?
I think this is JSON. This is just text, my friend.
It was a list of snail fish.
Okay, 11223344. Is that right? 11223344.
Yep. Looks good to me.
why did I close that? Input day 18.
I
30534455.
want to
Okay.
get part A done, and then I think I have to piece because this one this went a little longer than I expected.
No, totally. It was going way longer than I expected as well. Sorry to hold you. If you need a jet, please jet. 5074 5566.
Really close.
Yes. Here's a slightly larger example. We're just going through
we
examples.
get we got that. Great.
Yeah, we got it.
Cool.
The final number is 877786, 877786, 7707, 7707, 6687. And then let's see if the pairing kind of happened the way that we wanted. Everything, the pairing, I think the depth might be incorrect here, which is a problem.
I'm not sure it is. I think everything is at depth 3, except for the final pair.
Oh, you're right. 3333.
Mm-hmm. Yeah.
Yeah.
It's just complicated. It's just it's just weird, but yeah.
It's just weird and complicated. Okay, so let's talk about how we do the reconstruction then, right?
So this example is interesting because this is the one they use for magnitude. So maybe that's, I'm just going to try to talk us right out of trees.
Oh, you're saying we don't even need the tree again?
I'm curious. Well, if we're about to figure out how to break it up pairwise to reconstruct a tree from an array, then we don't need the tree. Because all we need to do is figure out left and rights of the array.
And so the way this works is that if you haven't figured out a pair, you know that there's a pair about to start, and you know that the one that you consume next is the left one. And if the node to the right of that has the same depth,
then you're a pair.
Then you're a pair. And now you don't have a pair.
And if you're not,
so if you're not, you do this recursive thing. Yeah. We have to basically make a stack, right? We have to make a stack. We just basically put that one on the shelf. And then go to the next one.
You keep counting until you find the next one of the same depth.
And then you pop off the stack when you actually find one, right?
Okay, so here's... Now, the interesting thing is that not everything has a pair, because you can have a pair of a single digit and a pair. So you can have a number, you can have an odd number.
Yeah.
Like, and that's interesting. Snail Fish, magnitude of the pair is 3 times.
I think you're right that we can write the scoring function without having to reconstruct the tree. It's just that we're going to end up like making the tree in like an intermediate, in an imperfect way, right? Do you just want to try it and then see, or we can?
I guess I'm really just trying to figure out if we can do a magnitude function period off the values array that we have. I'm not sure. Magnitude is recursive. So really, okay, so hang on. So for magnitude, you have to find two numbers that have the same depth next to each other and run the function on them. And that's it. Because you have to take the two numbers, figure out the magnitude of that pair, and then and
you're saying let's crunch the
and then you crunch it. So you find the first two numbers with the same depth, run the pair magnitude function, crunch them into the array as the multiplied number at depth -1, and do it again. I think that's
so we're basically going to reduce down until vals has basically one item in it. Is that what you're saying?
To a single number. Yeah. Yep.
Okay. So let's do
So it's really just any two consecutive numbers. That's all we're looking for in depths. That's very interesting.
Yes, for I in 0 to depths dot length -1, right? Let A equal depths I, let B equal depths I plus 1. If A is not equal to B, then we can continue. Oops. Otherwise, they are equal. And that means that they must be at the same level, right? If they're consecutive. Yes.
Yep.
So what we're saying here is that vals, so these need to be mutable again, right? We're doing a single score reduction. So vals of I is equal to vals of I plus. Oh, we have to do the score computation. What is the score again? Is it 2 times the?
It's 3 times the left. This is such a complex problem statement.
Yeah, it's very long.
It's
3 times the left
way-
plus 2 times the right element. Okay.
Okay.
I plus 1. And then we return true, right? Or should we just keep
Yeah.
looping until we get 1?
I think this is recursive.
Yes. Okay. Yeah. It's recursion iterations are 2 sides of the same coin. Now we actually need to delete the second value, right? So we do vals dot remove I plus 1, depths dot remove I plus 1,
and depths I minus equals 1, and then recurse.
and then loop again, right? So we don't need to return anything. I think what we're doing here is we break out of this loop. And we're just saying while val's length is greater than 1. And then we'd return val's 0. That was a very nice insight, Dominic. I think this is like a tree problem that isn't actually a tree problem. That is, I think, what
it really threw us for the first half.
Yes. Yes. This might actually be an area where I'm going to do. I think this looks a little bit better for some reason. Yeah.
Yeah, I wish we hadn't thrown. I feel like I maybe threw out your arrays suggestion too early. But I think you weren't convinced either.
Yes, let us not be hasty and pointing fingers. It's fine.
I don't think you convinced either of us because it's weird. It really looks like a tree problem.
It does look like a tree problem. Yeah. Okay. So now we can just call score on this bad boy, right? So we just print the score.
Print score vals, yeah.
And oh yeah, we got to mutate. Pisses me off that we're mutating, but you know what? I don't care. It doesn't piss me off. It makes me slightly uncomfortable. We're subtracting with overflow. Is it because depths can't equal 0? And if so,
what?
I think.
Is that our
That
very
is line
last
136, right? Yeah.
So like when we get to 0, do you want to just wrap that in if depth I is that this is like removing the final element, if that's what it is. If we've gotten to depth 0 for 2 elements. So you want to say if depth I is not equal to 0, do this.
Yeah.
Because
we'll basically have gotten we'll have basically gotten to the end if this gets down to 0.
It's got to be the final check, yeah. If depth I is greater than 0.
Yeah, if it's doing what we think it's doing, then this is the final check, then that's correct. So let's
3488. It's 4140.
Uh,
Oh no, it's 3488 here.
which one are we doing?
It's a different example. 4140.
Wait a minute.
Okay, that's cool.
Oh.
All right. So I
Oh,
think
you scared me.
Yeah. I think we've gotten to the bottom of this. 4469. Nice.
Nice indeed. Okay. Please.
All right. Woo, we got that one. Get out of here, Dom. You're good.
I want to see what
And
part two
I
is.
will I will carry the stream forward.
Wait, I want to see what part two is. Show me.
You want to at least see what part two is. Okay. Part two. What is the largest magnitude you can get from adding only 2 of the snail fish numbers? Note that snail fish addition is not commutative. That is, x plus y and y plus x can produce different results. Again, considering the last example assignment we have, the largest magnitude of the sum of any 2 snail fish numbers in this list is 39. Oh, this is easy.
I was gonna say, compared to what we just did, this is nothing. All right. Great.
Yes. Can we add the number? Can we add the same number to itself?
Oh,
Only 2 of the snail fish numbers. I'm going to say that you can't use itself.
I think that's right. Yeah.
All right. Do you want to do this with me? It's
No,
real. It's going to be real quick.
I'm gonna peace.
Okay. All right. Take it easy then.
All right.
Thank you, Dom.
Do you need
And
to
we'll talk to you later.
Do you need to change any stream stuff before I get out of here?
Let me add the other streamer back in, just so we don't mess up the layout really quick.
Yeah.
How do I even do that?
I think you like just right click into the screen.
Oh, show self view. Yes.
Yeah. All right, cool. Well, this
Okay.
was a journey,
Take it easy, Dom.
but
Yeah, it was a journey. Yes. All right. Take it easy, man.
I'll see you.
Okay, now that Dom is gone, we can actually start working on this. Just kidding. Gonna modify some code just to make sure I don't have any weird things here. Why does this think it's JSON? I guess it kind of looks a little bit like JSON, but this is plain text. All right, let's go ahead and revise. Let's go ahead and revise our previous commit. And then day 18B, we should have. Let's make sure that compiles. Oh, and it didn't get my change, which is fine because we're going to open this. We're going to reload the editor just to make sure that it recognizes the new directory. And now we can, that problem should pop back up again. It is weird that it didn't. I think it might have just kicked in. It just took it a while to rev up. Okay, so in this, we're just trying to do pairwise addition and then compare the scores. So what we're going to do here is we are going to record multiple trees into a vector. So, or maybe what we're going to do is just record. Yeah, that's what we'll do. We'll just make a bunch of trees. Okay. So let's do let trees is equal to input.lines. Well, we can do this now. Get input.lines .map. And there's a string that we're passing in here. And we will do parse of the line and just get the 0th value from that. And then we're going to collect that into a vector. Trees. Okay, now what we're going to do is we're just going to try to find the best pairwise score. So let mute best score, and it's going to be, let's just say I32 min, U32 min, or 0, right? Let's just say that the best score is like the lowest that we possibly can have. And now we are going to do pairwise, pairwise comparison. So we're going to just say let I in 0 to trees dot length, or for I, sorry, for j in 0 dot trees dot length, we are going to say that we're going to make an array tree. Boy, I wish I had made this a little bit more convenient to work with. Make array tree AV, AD, AV, AD. And the tree that we're using is trees I. Let's call it IV and ID. We're going to do it with J as well. And now we're going to get the score. Oh, we got to add these together. So first we're going to add array tree, IV, ID, JV, JD. And those are all mutable. Wish I had cleaned this up a little bit, but I'm a little bit eager to get done with this function. Let's take the score. So we'll just say that the best score is equal to the best score dot maximum of the score of IV and ID. And then we'll just print out the best score. We never use explode. That is not true. We need to do a reduction. I forgot to add a lot of code. After we add, we need to reduce. Use variable j. That's because j needs to be in here. Boy, that would have been a bug that I wouldn't be able to find for a long, long time. Okay, now let's give that a shot. It should compile 4770. I really hope this is it. And boom, we got it. All right, very nice. That was day 18. I think by far the trickiest problem that we've dealt with so far. Luckily, we were never totally lost. It was just a bunch of bouncing back and forth between different thoughts about different kinds of representations of this. But I think we were able to make it. I'm pretty satisfied with this answer, actually. If I was to change it, maybe I would clean up this data structure. So I was dealing with, oh hell, let's actually just, let's clean it up now. It's gonna make me feel a little bit better. Call it a vectory. Got a vectory. We're gonna derive, debug, and clone for it. And then from here, everything that takes a mutable pointer to a vec and a depths, I'm just going to call it the vectory. Let's call it T. Explode will work the same way. And making the array tree. Yeah, this is recursive, so I don't want to. It's a little bit annoying that we have to do it this way, but the vectory is going to be a mutable vectory. So far, so good. I think I got rid of the depth, which is a U32 here. Yeah. So why is the compiler not compiling? Let's go ahead and I think there's just like a straight up missing. Oh, this is not, this is a struct. What am I thinking here? Can I find vowels in the scope? That's fine. That's because we're using t.vals or vt.vals and vt.depths. This maybe actually makes the code a little bit harder to read because I'm just having to type vt dot everywhere. But that's okay. Oh, T. What? It was VT just in the function where I needed a regular tree and a vec tree. Let's actually call this make vec tree. Split is also going to take a tree, which is a mutable reference to a vec tree. And we'll do the same modification here. And also here. Actually, this is the first one where we're making our lives easier by just having the tree. It's a little bit less bookkeeping here. Add array tree. So we're going to have A and B. And this is every underscore is basically going to become a dot. And then the score, same thing. Let's actually go ahead and rename this to, no, rename this symbol to t.vals. It's going to complain about it. That's too bad. Oh boy, let me see if this will be a little bit easier if I be slightly smart about it. That's a lot better. And now we're returning t.vals. Yes, okay. So now we just need to make a vectory. Let's do vectory new. Let's make a little impl here. We're just gonna make a little new function that just returns a vectory. And it just calls vec new on both of these things. Like so. Let's say it's the I tree is equal to vec tree new. And this is a mutable reference to the I tree. And there's going to be a J tree. Let's make sure this is using the Jth tree. And then we are going to add the I tree and the J tree. We're going to reduce the I tree. And we're going to get the score of the I tree. No vowels here. Oh, I just forgot one T dot. And then if we compile again, hopefully we get the same answer, 4770. That's actually slightly slow. Okay, and that's a lot faster. Okay, now we finished and cleaned up day 18B. Wow, that was a huge pain in the ass, but really fun as well. I need to get on with my day, so I will talk to everybody later. See you for day 19, hopefully tomorrow.